You are standing in a control room in Pasadena, and the number on the screen in front of you says 23 hours. That is how long it will take a single word sent from this room to reach a machine older than most of the engineers reading it. Somewhere past the edge of the solar wind, a spacecraft the size of a small car is still listening. It launched before most of you were born. It is still answering. This is Deep Signal, and if stories like this one are your thing, the subscribe button is right there. Let's get into what is actually happening inside Voyager 1 right now, because the real story is stranger and more precisely documented than most of what gets said about it online. Voyager 1 left Cape Canaveral on September 5th, 1977, 16 days after its twin, Voyager 2, had already launched from the same pad. It rode a Titan III E Centaur rocket into the sky at 8:56 in the morning, Eastern Time, carrying a mission plan that gave it 4 years to live. 4 years to fly past Jupiter and Saturn, take pictures, measure magnetic fields, and finish quietly. NASA finished paying for that 4-year plan in November of 1980, when Voyager 1 completed its flyby of Saturn. Everything after that has been bonus time, and the bonus is now 46 years long. The spacecraft carries 10 identical science instruments built to study planets, moons, rings, and the charged particles drifting through space. It carries a gold-plated copper disc, the Golden Record, assembled under the direction of Carl Sagan, holding greetings in 55 languages, music from cultures across the planet, and a diagram showing where Earth sits relative to a set of pulsars, in case anything or anyone ever finds it. In February of 1990, on its way out of the solar system, Voyager 1 turned its camera around and took a photograph of Earth from about 7 billion miles away, a single pale pixel against a shaft of scattered sunlight. The image Sagan later called the pale blue dot. On August 25th, 2012, at a distance of roughly 121 astronomical units from the Sun, it crossed the heliopause and became the first human-made object to leave the heliosphere, the bubble of solar wind and magnetic field that the Sun blows around itself. It has been in interstellar space ever since. The 4-year plan produced results nobody on the original design team had fully anticipated. During its Jupiter flyby in March 1979, Voyager 1 photographed active volcanic plumes on the moon Io, the first confirmed volcanic activity ever observed anywhere in the solar system besides Earth. It found a faint ring around Jupiter that had never been detected from Earth-based telescopes, and it returned close images of moons that had previously been little more than points of light. At Saturn, in November 1980, it studied the planet's rings in enough detail to reveal structure inside them that ground-based observation had never resolved, and it made a close pass of the moon Titan specifically to study its dense, hazy atmosphere, a maneuver that bent Voyager 1's path northward, out of the plane the planet's orbit in, and effectively ended any chance of it ever visiting Uranus or Neptune. That trade-off was deliberate. Voyager 2, launched slightly earlier but on a slower trajectory, went on to fly past both those planets instead, while Voyager 1 became, by the accident of that single course change at Saturn, the spacecraft heading fastest and most directly out of the solar system. Every one of those instruments and every course correction since has depended on Voyager 1 doing something almost nobody thinks about, talking to the Deep Space Network, a set of giant dish antennas NASA operates in California, Spain, and Australia, spaced roughly a third of the way around the globe from each other, so that at least one is always facing the spacecraft as the Earth rotates. Commands go out from that network in one direction, and data comes back in the other, at the speed of light, which sounds instantaneous until you remember how far away Voyager 1 actually is. None of what follows in this video makes sense without that detail sitting in the background. Every single fix described from here on had to be planned, written, checked, and sent without the option of watching it happen in real time. None of that explains what is happening inside the spacecraft today. For that, you need to go back further than most coverage does, to a smaller warning sign the mission team got a year and a half before the big one. In May of 2022, Voyager 1 began sending back nonsensical data from a different onboard system, the Attitude Articulation and Control Subsystem, or AACS, the set of components responsible for keeping the spacecraft's antenna pointed at Earth. The numbers coming down did not match anything the spacecraft should have been doing, values that looked essentially random against what the team expected. Yet Voyager 1 itself seemed to be behaving normally in every other respect, still oriented correctly, still receiving commands, still able to phone home on schedule. That mismatch, a spacecraft that appeared to be functioning while its telemetry insisted otherwise, was itself a diagnostic clue. Engineers eventually traced the fault to the AACS, sending its telemetry through a different onboard computer than intended, one that had, itself, stopped working correctly sometime earlier, garbling the readings before they were transmitted, even though the AACS was carrying out its actual job correctly the entire time. The team resolved it by rerouting the AACS data through a working computer, and by autumn of 2022, Voyager 1 was reporting normally again. At the time, it read as a solved problem, a strange one, but a closed case. In hindsight, it was the first sign that Voyager 1's aging computer systems were beginning to fail in ways that would require increasingly creative workarounds to even properly diagnose, let alone fix. On November 14, 2023, the spacecraft's signal changed. It was not silence. The radio link stayed connected, the carrier tone stayed steady, and Voyager 1 kept receiving commands exactly as it should. But instead of the structured stream of science and engineering data the mission team expected, they were getting a flat, repeating pattern of ones and zeros. Suzanne Dodd, the Voyager project manager at NASA's Jet Propulsion Laboratory, later described it to Scientific American as the most serious problem she had faced in her time on the mission, precisely because you can lose meaningful contact with the spacecraft without losing the connection itself. Engineers compared it at the time to a phone call that was still connected, except the voice on the other end had been replaced with a dial tone. The suspect was a system called the Flight Data Subsystem, or FDS, one of 3 onboard computers, and the one responsible for packaging Voyager 1's data before it gets handed to the telemetry modulation unit and broadcast home. The trouble was diagnosing a computer from 15 billion miles away using a command language written for hardware that predates the personal computer, with every test cycle costing roughly 2 full days, 1 day for the command to arrive, 1 day for a response to come back. For the first 3 months, that back and forth produced nothing conclusive. Engineers tried cycling different combinations of instruments on and off, hoping to isolate the problem by process of elimination, and it did not work. So, in March of 2024, they escalated, ordering a full memory readout of the FDS, essentially asking the computer to report back everything stored inside it, piece by piece, so the team on the ground could inspect it directly rather than guessing from the outside. That readout is what finally found it. A single chip, storing about 3% of the FDS memory, including code the system needed to package data correctly, had stopped functioning. Nobody could say with certainty why. It might have been struck by a high-energy particle from space, the kind of event spacecraft in interstellar space are more exposed to than anything orbiting Earth. It might simply have worn out after 46 years of continuous operation. Voyager's propulsion engineer, Todd Barber, later described the ongoing work of keeping these 2 spacecraft alive to IEEE spectrum in blunter terms, calling it palliative care for what he called 2 positively geriatric spacecraft. Voyager 1 was not the only one of the pair having problems that year. Voyager 2 had its own scare in mid-2023 when a planned command sequence accidentally pointed its antenna 2 degrees away from Earth, cutting off contact entirely for about 2 weeks until a scheduled autonomous reset pointed it home again on its own. The 2 incidents were unrelated in cause, but together they underlined the same point. After 46 years, the margin for error on both spacecraft had become vanishingly small, and problems that would have been minor annoyances in the 1980s now carried the possibility of permanent silence. You cannot fly a repair technician to a spacecraft in interstellar space, so JPL's engineers did the next best thing. They could not restore the chip, so they broke the code that had lived on it into smaller pieces and found empty space elsewhere in the FDS memory to store them, effectively rewriting part of Voyager 1's operating instructions from a control room on Earth. On April 18, 2024, they transmitted the first piece of that patch. It took about 22.5 hours to arrive. 2 days later, on April 20th, the team got back a signal they could read again. Readable engineering data followed almost immediately. Science data, which required a second and more delicate set of commands, came back in stages through May and June of 2024, with 2 of Voyager 1's 4 working instruments returning to normal operation right away, and the remaining 2 needing further adjustment before all 4 were confirmed to be sending usable data again. It is worth being precise about what the fix did and did not do. It did not repair the chip, which remains permanently unusable. It relocated the working code around the damage, which is a very different and much more fragile kind of solution, one that depends on there being enough spare memory left to keep doing it. Spare memory is not the spacecraft's real constraint. Power is, and it always has been. Voyager 1 runs on 3 radioisotope thermoelectric generators, devices that contain no moving parts and burn no fuel in the conventional sense. Instead, they convert heat given off by the natural radioactive decay of plutonium-238 directly into electricity, using a solid-state process that has no engine to wear out and no combustion to sustain, which is a large part of why the hardware itself has lasted this long. The trade-off is that plutonium-238 decays on a fixed physical schedule nobody can slow down or negotiate with. At launch, the 3 generators together produced roughly 470 watts. Radioactive decay does not stop for anyone, and the mission has been losing about 4 watts of available power every single year since 1977, a curve that is entirely predictable and has been factored into the mission's planning since before the spacecraft ever reached Jupiter. By early 2026, output had fallen to somewhere in the range of a couple hundred watts, enough to run a couple of large light bulbs, distribute across a spacecraft that has to keep its instruments and cold, sensitive electronics warm enough to survive temperatures near minus 270 degrees Celsius in interstellar space while still doing science. Engineers have been managing that decline since the late 1990s, in a fixed order that the science and engineering teams agreed on years in advance, shutting off one system after another, starting with the ones that matter least to the mission's remaining goals. The heaters go first when they can, then instruments judged least essential to the interstellar science still within reach. And only as a last resort, anything touching the spacecraft's ability to point its antenna at Earth or receive commands at all, since losing that would end the mission outright regardless of how much power remained. It is a budget managed the way you might manage a battery on a phone that will never be recharged again, except the phone is 46 years old, cannot be replaced, and every decision about which app to close has to be made a full day in advance, sent across billions of miles and confirmed a full day after that. On February 27th, 2026, during a routine, planned roll maneuver, something happened that had not been in that careful plan. Voyager 1's power levels dropped further than expected. Mission engineers understood the risk immediately. Any additional loss could trigger the spacecraft's undervoltage fault protection system, a piece of onboard automation designed to shut down components on its own if power runs dangerously low in order to protect the spacecraft from itself. That kind of automatic shutdown is not something the team wants to happen unsupervised, because recovering from it at a 2-day round-trip communication delay is a long and uncertain process. So the team decided to act first, rather than wait to see whether the fault protection system would act for them. The decision was to turn off the low-energy charged particles experiment, known as LECP, an instrument that had been running almost continuously since 1977, measuring ions, electrons, and cosmic rays from both the solar system and the wider galaxy, and one of the tools that had let Voyager 1 detect pressure fronts and shifting particle densities in interstellar space, a kind of data no other spacecraft is positioned to collect. On April 17, 2026, JPL sent the shutdown command. Because Voyager 1 was, by then, more than 15 billion miles from Earth, the command took roughly 23 hours just to arrive, and the shutdown sequence itself ran for a further 3 hours and 15 minutes once it did. Kareem Butterudin, the Voyager mission manager at JPL, put it plainly in NASA's own announcement. Shutting down a science instrument is not anybody's preference, but it was the best option available. Voyager 1 was left with 2 operating science instruments, one that measures magnetic fields and one that listens to plasma waves, both of which, as of that announcement, were described by the mission team as still working well. That is not where the story of Voyager 1's power ends, though. Turning off one instrument at a time buys months, not years, and both spacecraft are running out of things left to turn off. Of the 10 identical instrument sets each Voyager originally carried, 7 had already been switched off by the time LECP joined the list, which meant the usual playbook was close to exhausted. So the team has a longer-term plan, one they have nicknamed the Big Bang, and it works differently from anything attempted on these spacecraft before. Instead of shutting one system down and leaving the rest of the spacecraft's power configuration untouched, the plan calls for switching some currently active systems off, while simultaneously switching on lower power alternatives that can perform similar functions, all in a single coordinated operation, rather than the slow, one-at-a-time, shutdowns the mission has relied on for decades. The appeal is that it could free up a meaningfully larger amount of power in one move than another individual instrument shutdown ever could. The risk is exactly what you would expect from rewiring the power configuration of a 49-year-old spacecraft in one shot, with no way to walk the change back gradually if something goes wrong. Because a mistake could be catastrophic, and because there is no possibility of physical repair at 15 billion miles, the team chose to test the maneuver first on the safer of the 2 probes. Voyager 2 has slightly more power in reserve and sits closer to Earth, which makes any command sequence faster to send and any recovery attempt less drawn out. Tests on Voyager 2 were scheduled for May and June of 2026. If those tests succeeded, the plan was to attempt the same maneuver on Voyager 1 no earlier than July of 2026, a timeline that, as of this video, is either underway or about to begin. There is even a chance, according to NASA's own reporting on the plan, that a successful Big Bang maneuver could allow the LECP instrument on Voyager 1 to be switched back on at some point in the future. Though the mission team has been careful not to promise that outcome, and nothing about the maneuver has been described as low risk. There is one more milestone sitting on the calendar, and it has nothing to do with instruments or power. It has to do with distance. On November 18th, 2026, at 2:16 and 7 seconds in the morning, Pacific time, Voyager 1 will become the first human-made object to reach a distance of 1 light day from Earth, a point where radio signals traveling at the speed of light take a full 24 hours to cross the gap in either direction. A light day works out to about 25. 9 billion kilometers, or roughly 16. 1 billion miles, calculated simply by multiplying the speed of light by the number of seconds in a day. Susie Dodds summarized what that means for the people running the mission in a comparison that has been widely quoted. If you send a command and say, "Good morning, Voyager 1," at 8 in the morning on a Monday, you get the response back at approximately 8 in the morning on Wednesday, since the outbound leg takes a full day and the reply takes another day to return. It is worth being clear about what this milestone is and what it is not. Voyager 1 will not be leaving the solar system in any final sense on that day. It already left the heliosphere, the sun's bubble of solar wind and magnetic influence, back in August of 2012, and the sun's gravitational pull, along with the outer edge of the Oort cloud, a distant shell of icy debris still loosely bound to the solar system, extends vastly farther than one light day, likely for trillions of kilometers beyond it. NASA's own materials on the milestone are careful to frame it this way too, describing Voyager 1 and Voyager 2 as the only spacecraft to operate outside the heliosphere, not as craft approaching some other star system. What crosses on November 18th is a threshold of communication time, not a boundary of space itself, but it is still a real number and a real first for a machine that was never expected to still be listening this far out, and it means that for every operation the Voyager team runs on this spacecraft from that date forward, the absolute minimum wait time for any two-way exchange is 2 full days, a constraint that will only keep growing as the distance keeps climbing. Here is where this stops being a story about a spacecraft and starts being a story about what it takes to keep any long-duration mission alive. Voyager 1 is not surviving because 1970s engineering was somehow indestructible. It is surviving because a small, specific team has spent decades making deliberate, irreversible trade-offs in a fixed order they agreed on years in advance. And because every fix has to work on the first try, since there is no way to send a technician and no way to test some of these repairs on an identical unit here on Earth, because the ground-based equivalent hardware is itself decades out of date. That approach, plan the shutdown order years ahead, test risky changes on the lower stakes. Twin first, treat every command as if it might be the one that does not come back, is not just a curiosity from one aging mission. It is a working reference for engineers designing spacecraft today. NASA and its partners are actively planning missions meant to operate for decades in environments where repair is impossible and communication delays run into hours, from long-duration orbiters around the outer planets to any future probe aimed at interstellar space itself. Every one of those designs has to answer questions the Voyager team has already been answering in practice for years. How do you decide, years in advance, exactly which capabilities to sacrifice first and in what order? How much spare memory or spare power margin do you build in for problems nobody can predict yet? How do you test a fix on hardware you cannot touch? None of this changes the physics of the outer solar system or overturns any established science about the interstellar medium. What it demonstrates in a very literal and ongoing way is how far careful, conservative engineering and a willingness to make hard, irreversible cuts on a schedule can stretch a machine's working life past every original estimate for it. Voyager 1 was designed to survive 4 years. It is closing in on 12 times that. So where does that leave the spacecraft right now? As of the most recent mission updates, Voyager 1 is operating with 2 active science instruments, the magnetometer and the plasma wave subsystem, both still returning usable data from a region of space that no other functioning spacecraft occupies. It sits somewhere past 15.5 billion miles from Earth, a distance that grows by roughly 3.5 astronomical units, more than 500 million kilometers every year, and is closing in on that one light day threshold set for November 18th, 2026. Its twin, Voyager 2, is trailing behind at a shorter distance, currently estimated at around 13 billion miles out, and running with 3 active instruments rather than 2, a small but meaningful gap that exists only because of the different order in which each spacecraft's shutdown list is played out. Both probes are still moving outward at interstellar cruising speed, Voyager 1 covering roughly 38,000 miles every hour, and both are still, as of this recording, checking in with the Deep Space Network on their assigned schedule. Voyager 1's course, its instrument shutdown order, and its power budget are all managed on a schedule the mission team set years in advance, and the attempt to apply the Big Bang power maneuver to Voyager 1 itself, following whatever results came out of the Voyager 2 tests in May and June, is expected to take place no earlier than this July, which places it right around the time this video is being published. Nobody on the Voyager team is pretending this continues forever. Current estimates from JPL suggest the spacecraft's power supply will fall below the minimum needed to run any remaining instrument sometime in the early 2030s, though the mission has already outlived multiple earlier predictions of its own end, so that date should be read as an estimate, not a deadline carved in stone. It is also worth remembering that the LECP shutdown itself was not originally scheduled for this point in the mission timeline. It was moved up because of the unplanned power drop during that February roll maneuver, which means the team's own long-range schedule has already had to bend once this year to an event nobody predicted, and it may have to bend again. What happens after the power finally runs out is, in its own way, simple. Voyager 1 does not fall, and it does not stop. It keeps moving outward, carrying the golden record with it, and it will keep doing that for an effectively unbounded stretch of time, whether or not anyone on Earth is still listening. The open questions between now and then are practical ones, not dramatic ones. Will the Big Bang maneuver work as well on Voyager 1 as it did on Voyager 2? Will the LECP instrument ever come back online, as the mission team has said is possible but not guaranteed? Will the spacecraft's aging fault protection systems handle the next unexpected power dip as cleanly as they handled the one in February? And when the final instrument does eventually go dark, will the spacecraft's basic carrier signal, the simple radio tone that confirms it is still there even without any science data attached, keep transmitting a while longer, the way engineers currently expect it might? Nobody in that control room in Pasadena knows the answers yet, and given the growing weight on every single command, they may not know for days after they find out. What stays with you, after all the numbers, is not a message sealed in a bottle drifting toward some hypothetical reader. It is the opposite. It is a machine still being actively operated in real time by people who write commands in an assembly language most working engineers have never touched, who wait 2 full days to learn whether a fix succeeded, and who have spent decades deciding, one deliberate shutdown at a time, exactly how a 46-year-old spacecraft should slowly go quiet. Picture the actual sequence of what happens on a day like that. Somewhere in Pasadena, a small team finalizes a command they have checked and rechecked because there is no undo button 15 billion miles away. And that command travels outward at the speed of light for the better part of a full day, crossing a gap that keeps growing every single time it is sent. It reaches a spacecraft running on a fraction of the power it once had, built from components no factory still makes, executing instructions written in a programming language most of today's software engineers have never opened a manual for. Voyager 1 responds, if it can, and that response begins its own day-long crossing back toward Earth, arriving in a control room where a handful of people, some of whom started their careers on this exact mission decades ago, listen for a signal that tells them whether 4 decades of careful, layered decisions just held one more time. That is the machine, not a wandering ghost, not a silent artifact. An active, working piece of hardware, still on the clock, still checking in. Voyager 1 is not a monument. It is a conversation that has been running since 1977, getting slower and more expensive with every passing year, and as of this video, it has not ended yet. If you want more of these deep dives into the mission still running at the edge of what we've ever built, subscribe for the next one. Tell me in the comments which part of Voyager's story you didn't know before today. And if this helped you understand what's actually happening out there, share it with someone who still thinks Voyager 1 went quiet years ago.